Hi everyone, today we're going to be talking about topic 1.7, periodic trends. So before we get into all those periodic trends, we kind of have to understand what's known as Coulomb's law, which is going to explain a lot of the trends that we're going to be speaking about today. So Coulomb's law is an equation, but we're not necessarily going to be solving this equation ever in AP Chemistry. But what it says is that F, or the force of attraction, is equal, or not equal, is proportional. I'm going to use this proportional symbol here, right, because we're not actually solving it. We're just talking about some trends. The force of attraction of two, ions, of two particles, of electrons, whatever it may be, electrons, protons, is proportional to the charge of one, or Q, times the charge of the other, or Q2, over the radius squared, or the distance squared. And so distance slash radius, and Q is equal to the charge of the ion, particle, etc. Right? And so if we're thinking of attractive forces in an atom, right, Q1, this would be our electron, Q2, this would be our proton, and if we're thinking of ions, right, we can think of those as either the cation and the anion in an ionic compound. If we want to visualize r squared, or the radius, we can think of one particle here, one particle here. Let's say this is a proton, and right here we have an electron. Its radius would be this distance right here, the distance between the center of both of those particles. And our force of attraction is inversely proportional, meaning that if you increase the radius, you're going to be decreasing that force of attraction. Or in other words, if the electrons are far away, from the protons, then the attractive force is lower. Which makes sense, right? If you put the two particles away from each other, the two charges, they're not going to be able to pull on each other as much anymore. Now, something on that last worksheet that I handed you that you may have seen was something called ZEF, or Z effective, also known as the effective nuclear charge. What this is, it's the charge acting on the outside electrons. And by definition, the effective nuclear charge, ZEF, or Z effective, ZF, is calculated as ZF equals number of protons minus the number of inner electrons, or E minus. Right, and so if I want to, for example, calculate ZEF for aluminum, what I would do is I would look at the number of protons of aluminum, which is 13, and subtract the number of inner electrons. So if we look at the electron configuration of aluminum, we have 1s2, 2s2, 2p6, 3s2, 3p1. Right, and so in this case, our outer shells are in the third energy level, and so this 3s2 and 3p1 would be our outer electrons, and therefore 2, 2, 6 of 1s2, 2s2, and 2p6 would be our inner electrons. And so therefore it'd be 13 minus, altogether in parentheses, 2 plus 2 plus 6, which is equal to 13 minus 10. And so our effective charge being felt by those outside electrons is going to be 3. And what you might be able to notice from this trend is that if we go down the period from sodium all the way to argon, and this happens for every single period of the periodic table, when you calculate Z effective, if this is Z effective, it increases as you go down the period. So ZEF for sodium would be 1, Zeph for aluminum is 3, for silicon it's 4, for phosphorus it's 5, so on and so forth. And so what this is telling us is that sodium feels a weak positive force from the nucleus, and argon feels a strong positive force from the nucleus. And we're going to just see in the next couple slides how Zeph kind of plays a role into all of our different periodic trends that we're going to be talking about. So here is periodicity, all the different trends that we're going to be talking about. Periodicity is the repetitive pattern of a property of elements, and so there's a few that we typically like to talk about: atomic radii, ionic radii, ionization energy, electron affinity, and then finally electronegativity, all of which kind of help us predict the reactivity of elements or compounds, elements on the periodic table, or compounds made from those elements. And as another reminder of Coulomb's law, I had said previously that Coulomb's law is kind of this relation here, where we're talking about Q1, this would be our proton, and this would be our electron. You can also think of it as in terms of Zeph, and so the force of attraction between two particles, whether that be proton or electron, or between two ions, thinking if you're thinking of maybe sodium chloride, the sodium plus and the chloride minus, Na plus and Cl minus, it would be Zeph divided by the distance squared, and so you'd calculate Zeph for both of those and then divide it by distance squared. So the first of the trends that I want to talk about is atomic radius. And so here are kind of two graphs depicting what atomic radius looks like and what those trends are. So we're looking here on the left, this graph is saying is that as we increase in atomic number, we have these jumps in atomic radius. And if you notice, right here is where we have lithium, this peak right there. It continues down, 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 and down until this final one here is where we have neon. And then it jumps once again when we get up to sodium. It decreases once again, and then when we get over to potassium, K, it once again increases in radius. Finally continues to go down, 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 and down until it reaches this plateau, and then once we finally get over to rubidium, we see that increase again. And if we're looking here at this table of atomic radii, what we can see is that radius decreases as you go to the right, or as you increase the atomic number, and then it increases as you go down, which kind of makes a little bit of sense when we think of Zeph, right? Zeph tells us that there's a stronger positive force as we're going to the right, and a weaker positive force all the way to the left. And so as Zeph is increasing down the period, we see that the radius is also decreasing because those outer electrons are feeling much more of a positive pull from the radius. But as we're going down, from hydrogen to lithium to sodium, as we're going down, we're gaining energy levels. And so there are new orbitals for electrons to go in. And because those new orbitals are typically further and further away from the nucleus, you increase in size as you go down, and because Zeph is increasing across the period, your radius is also decreasing because you're feeling a greater positive force. When we can think of atomic radius, we're not only thinking about atoms on their own, right? Atoms typically make different molecules, and so you can also think of the bonding atomic radius. And this has a similar trend. So the bonding atomic radius decreases from left to right across a period. So as we're going down, it's decreasing. Or as we're going across, it's decreasing. And it increases from top to bottom. So as you go from hydrogen down, you have a compound with these elements in it. The bonding atomic radius is increasing as you go down the periodic table. And this bonding atomic radius is defined right here, where essentially, I'm going to use a red pen instead. You're looking at the distance here between one of your nuclei halfway to the other nucleus, right? And so if you had NaCl, that bonding radius would be right there for chloride, and right there for sodium. It's half the distance between the nuclei of each of your two atoms in your molecule. Another thing, it's extremely important whenever you're making a justification, say on the AP exam or on one of the exams in class, that you make the justification of the trend instead of just stating the trend. It's not enough to just say, atomic radius decreases as you go across a period. What you need to do is justify it. And a great justification, again, I'm going to keep bringing it up, is Zeph. It's a great justification. So the effective nuclear charge increases, which draws electrons closer to the nucleus, right? You can always think about Zeph when we're thinking about these periodic trends, and it is going to be a pretty good answer in every case, a pretty good justification. But you always have to spell out, right? Because it's drawing electrons closer to the nucleus. That's why the radius is decreasing. You cannot simply say the radius decreases as you go across a period. That is not a justification. And then additionally, like I had said, as you're going down the periodic table, right, you're adding new energy levels. And this is increasing the atomic radius, and that would be our justification. The next trend we're going to be talking about is ionic radius. And so in ionic radius, right, we're not talking about atoms anymore. Now we're talking about ions. And so in comparison to parent atoms, cations are going to be smaller than their parent atoms. And this makes sense, right? We've removed electrons. So if we take E- and we remove it, that means we have more protons than electrons. And so the repulsion between electrons, right, because electrons don't like to be near each other, you have two negative charges, they want to push each other away, goes down because we have less electrons. But then the attraction between the protons and the electrons goes up, right? Because now we have more protons than we have electrons. So those protons are drawing those electrons in, right? If those electrons are going closer to the nucleus, your radius, or R, should be going down. The reverse is true for anions, right? In the case of anions, and so right here, I'm going to write cations. For anions, right, repulsion between electrons is going to be increasing because we have more electrons are going to be pushing on each other. And here are just some examples of ionic radius, right? In class, we had talked about this term before, isoelectronic series. This just means same number of electrons. It's important that we understand what this terminology means in case we ever see it on a question in an exam or on the AP exam. And so down here in this table are just some examples. We have increasing nuclear charge, essentially Zeph is increasing here. And then what we have is the same number of electrons, O2-, F-, Na+, Mg2+, and aluminum 3+. And you can see the number of protons is increasing. The number of electrons is staying constant, but because we have, right, protons are increasing, attraction is increasing, and therefore size or radius should be decreasing because those protons, that nuclear charge is pulling on the outer electrons stronger than the ion before it. And again, we always need to remember our rationale. Anytime you're answering a question on periodic trends, you have to give a rationale. You cannot simply state the trend, right? And so the effective nuclear charge is increasing while electron repulsion is decreasing. That would be our reason for cations being smaller than the parent atoms. And for anions, the effective nuclear charge is decreasing while the electron repulsion is increasing, right? So in this case, Zeph, I'm going to keep bringing up Zeph, going up. In this case, Zeph is going down. The next trend we're going to be talking about, the third of the five, is ionization energy. So this is the energy required to remove an electron, right? And so an electron is being removed, usually to form an ion from the ground state of a gaseous atom or ion. And so the first ionization energy is what's required to remove that first electron, right? And so if we're thinking of sodium, right, that would be that 3s1 electron. That's that first ionization energy. The second ionization energy is the energy required to move the second electron. And so you have Na+, it would be removing that 2p6 electron right there. The higher the ionization energy, so high, we're going to call ionization energy IE, the harder it is to remove an electron. Right, and so very low ionization energies, the electron is very easy to remove. Very high ionization energies, that electron is difficult to move. And then once all those valence electrons are removed, right, and so now it looks like a noble gas configuration. It takes a great deal of energy to remove that electron, right? Because all atoms, no matter where they are on the periodic table, really want to achieve that noble gas configuration or something close to it. So here's a table of first ionization energies. You don't have to actually memorize this entirely. You just need to understand the trends here, right? Like I said, for sodium, that first ionization energy is pretty low, 496. But as soon as it gets that noble gas configuration, noble gas config, it no longer wants that electron removed because now it's going to be sodium 2+, and we never see sodium 2+. That's very unstable. It's very happy being at the sodium plus stage. And as you continue on, you can see magnesium. That first one is pretty easy to remove. The second one is a little bit harder to remove. And for pretty much every single other one you see here, that trend always follows. That first electron is very easy to remove, and as you continue to go on, they become very difficult to remove. Argon, right, you're hardly ever reaching this amount of energy to remove an electron from argon. So once again, let's look at our trends here. First ionization energy, generally it increases across a period. And then decreases down the group. Right, and so this trend is the opposite of Zeph and atomic or ionic. Really just atomic radius. Right, and so as the radius is decreasing across the period, the first ionization energy is increasing, right? Your radius is getting smaller, those electrons are getting closer to the nucleus, and it's becoming harder and harder and harder to remove those electrons from that outer shell. And then again, we always need a rationale. I'm not going to go super into depth into this because you can read it and kind of absorb it on your own. But whenever we're talking about any of these periodic trends, we always need to provide a justification. We can never just state the trend. And so read this, think about what that justification is and why it applies for ionization energy. The fourth we're going to be talking about is electron affinity. So electron affinity is the energy change accompanying the addition of an electron to a gaseous form. Right, and so if you have some sort of an element, whatever it is, X, you add an electron, it becomes X minus in the gas phase. The electron affinity describes the energy that changes once you add that electron. So here's some examples here. For fluorine gas, you add one electron to F gas, you get F1 minus, and that amount of energy is minus 328 kilojoules per mole. So for lithium, it would be minus 73 kilojoules per mole. And so it's basically a neutral atom's likelihood of gaining an electron, right? Right? If it's really, really high, or if it's more negative, then that means that there's a greater attraction for that electron. It will accept the electron better. But if it's less negative, it won't accept that electron. Right, and this makes sense, right? For fluorine really, really likes electrons. It's close to a noble gas configuration, and so it's going to want that electron. And in the next periodic trend, we'll talk about this a little bit more. Lithium, for example, it's really close to also being in its noble gas configuration, but it needs to lose an electron. It definitely does not want to gain an electron and become further away from a noble gas configuration. Now, unlike the trends we were seeing before, there isn't much of a change as we go down the group. You can see at hydrogen, the electron affinity is minus 73. For rubidium, it's minus 7. That isn't really that drastic. Although if we're going across the period, that's when we see these great differences. And so for hydrogen, Actually, we'll go down to lithium. For lithium, it's minus 60. And when you get to fluorine, it's minus 328, right? Fluorine is really okay with accepting that extra electron. It's perfectly happy with it. Lithium does not want to accept that electron. And one thing to note is that if the electron affinity is positive, like in beryllium, magnesium, or all of the noble gases here, that means that the anion that's made is very unstable, which makes sense, right? If we look at our sublevels here, for group 2A, beryllium, magnesium, calcium, strontium, or I should just say beryllium and magnesium, they're positive because, right, that S sublevel is full. As we get down to calcium and strontium, we also have the d orbitals, and those kind of change things around a little bit, since those, the d orbitals are okay with having a little bit more electrons. But if we also look here, if we look here at the noble gases, we can see those really do not want to accept any new electrons, and so they are very unstable as soon as you put an electron into its orbital. Once again, the rationale, make sure whenever we're answering a question on electron affinity or any other periodic trend that we're stating a justification and not just stating what the trend is. We want to understand why, fluorine is much more likely to accept an electron than lithium is, and not just state that that is the trend. Okay, and the final one, electronegativity, which is often used a lot when trying to understand kind of how different elements are reacting. So this is the ability of an atom or molecule to attract electrons to itself. And so this, similar to, it's a little bit similar to electron affinity, but as you go down the group, electronegativity decreases, and as you go across a period, it increases. And so the highest electronegative element is fluorine at 4.0, and the least electronegative element is cesium at 0.7. What this basically says is at high electronegativity, it likes electrons, right? It's okay with accepting electrons. If there's a bond between fluorine and cesium, for example, the electrons are really going to be on the side of fluorine. And low electronegativity, it does not like electrons. It's okay with losing those electrons or giving more of its electrons to a more electronegative element in something, say, like cesium fluoride. That's an ionic bond right there. The electrons in that bond are really completely on the fluorine, and they aren't on the cesium. I should say the valence electrons in that case. But if you have something, like a carbon and a hydrogen bond, right? Those are close together, and that's where we see more covalent bonds where those electrons are shared. And finally, once again, for electronegativity, we always need to state that rationale. We always need that justification. So from left to right, we're thinking again about nuclear charge. Zeph, right? Nuclear charge is our Zeph. That's increasing as you go down the period, and so the attraction atoms have for valence electrons also increases. And the reverse is true when you go down the group, right? There's an increasing number of energy levels, and the electrons are further and further away from the nucleus, so they're held less tightly, and therefore they really don't care about having that many electrons because they're not going to be close to the nucleus of those larger ions or atoms anyway. So finally, I have a little practice problem here for you. This is asking which atom has the largest atomic radius. And so if we're thinking of this in terms of Zeph, effective nuclear charge, right? As Zeph goes up, radius, or R, should be going down. As Zeph goes down, radius should be going up. So as we go across the period, right, Zeph is increasing, so radius should be decreasing. So if we're looking for the largest atomic radius, it should be towards the left side of the periodic table. Right, if we look at all of our atoms here, we look at selenium, that's really towards the right of the periodic table. Bromine is pretty much all the way to the top right of the periodic table, and so that's likely going to be a small atomic radius. Lead also is all the way to the right. Silver is, somewhere in the middle. And if we look cesium, right, that one is all the way to the bottom left of our periodic table, right? If we're thinking in terms of effective nuclear charge, all the way to the left should have the largest atomic radius. And as you go down, right, we're getting new energy levels. And so radius should be increasing. Cesium is all the way at the bottom left of the periodic table, and so that is going to have the largest atomic radius. So in class, we're going to do a little bit more practice problems and kind of think about this a little bit further. Other than that, thanks for listening.